Welcome to week 7, our final week, where we are working with graphs. And I chose to do my graph in C++ and did find out it was a little bit more work than I think Python would have been, but it was worth it. And I learned a lot out of it, especially working with the Boost library and getting it installed correctly and working with my program. And I also wanted to mention that to get the program to correctly run, I was not able to use my favorite namespace savers and instead had to use all of the namespaces as standard. But it works and just required a little extra coding in some areas. In this example, mainly to get the vector to work, and also, it was in the tuple. That's where else I had an issue with it not wanting to read without it being coded standard. But the rest of the code is very, very clean and simple in its essence for the most part. And it uses Dijkstra's shortest path. And it also calculates the breadth first search from any source city. And we will also be looking at the results of the connected components. So without any further ado, let's run our program. And we see that we are greeted with a GUI of our graph analysis menu. And it gives us an option of what we would want to do. So to run Dijkstra's shortest path, we select option 1. And we're given 20 cities to choose from, each one assigned a random numerical value that will be representative of it as if it were logistically on a map. So let's say we were trying to navigate from a city to another city. Well, let's see what city is city 0. Well, city 0 is New York City. And it calculates with Dijkstra's shortest path all 20 cities in our vector that it would have to calculate the distance with Dijkstra's method. And we get a value of units, which is just a value that is somewhat representative of miles, just a representation of distance ultimately between the cities, so that we actually do see a different value to get to these cities based on the route that they would take. So again, if we wanted to use Dijkstra's shortest path and see another city, let's choose city 13. And that is Buffalo, New York. And again, it calculates out each distance. And logistically, we can see that if we know geographically, say a close city to Buffalo, Buffalo to Pittsburgh is very close. But Buffalo to, let's say, Buffalo itself is 0 units. So it's calculating that it doesn't take anything. Let's say we wanted to go way away from Buffalo. Well, Chicago's pretty far away from Buffalo, and that is 803 units. And St. Louis is even further away at 940. So we can see that it's calculating out an actual numerical value representative of each one of our cities. And if we wanted to run the breadth first search, we again enter our city ID. Well, let's go back and look at Buffalo again, which was city 13, and the BFS levels. And what this shows is the edges on our graph and how many edges from each this would be away. So Buffalo from New York is 1 edge, Buffalo to Boston is 2, Buffalo to Philly is 2, to DC is 3, to Baltimore is 4. So you can see a path that it's taking there. To Pittsburgh is 1, to Cleveland is 2, to Detroit is 3, Chicago 4, St. Louis 5. So it's taking another path that way. And again, we can see it's calculating that Buffalo to Buffalo is nowhere. It's not going anywhere. It's 0 edges away. So we know that it is calculating out correctly. Let's go back and let's find the connected components. And in this graph, we have one connected component. And that is all of our components. New York to Boston to Philly to DC to Baltimore to Pittsburgh to Cleveland, Detroit, Chicago, St. Louis, Indianapolis, Cincinnati, Columbus, Buffalo, Toronto, Montreal, Ottawa, Quebec City, Richmond, Raleigh. Just a bunch of random city names, but all calculated out within our graph. And if we wanted to exit our program, we simply exit our program by selecting 4, and we are out of our program. And that concludes using Dijkstra's method in a C++ console application to navigate and use an algorithm to find a shortest route. I thought that was a lot of fun. I actually want to do more. We'll see. Thank you.